All right, guys, so I'm making this video just as a refresher on Gen Chem 1 stuff, and everything in here you're going to need for Gen Chem 2, basically. So let's just go ahead and go over some stuff. So this is the periodic table, and this trend up and to the right is an important trend for all of chemistry. It's the trend of electronegativity. And basically, atoms which are in this high up area or to the right in general and upper area in general, they attract electrons. Oops. Attract electrons. And you might have already known this, but you want to know like a little bit more about it, right? So in bonds, here are 3 bonds: OH, NH, and FH. These bonds are actually, these 3 elements, when they're with hydrogens, they're called hydrogen bonds. You'll learn about those pretty soon. But what happens between these bonds is that the elements here, they belong to this part of the periodic table, right? If you pull up a periodic table, they're in the upper right corner, while all these hydrogens are like in the polar opposite. They're like over here. So what happens when these bond is that they create pretty strong bonds because they have opposite affinity for electrons. So oxygen, nitrogen, and fluorine are really going to want electrons, and hydrogen is more electropositive and it's willing to share its electrons with these guys. So that creates something that we call a dipole. And a dipole is something that you draw on bonds. For example, oops. For example, here on the OH bond, you would draw a dipole like this. And the dipole basically represents 2 things. The head, which is the arrow part, it's going to show the direction that's attracting electrons. So the head here, that's the direction which the electrons are being attracted in. And this part right here that looks kind of like a positive sign or whatever, this part, it's where the electrons are being attracted away from. So since they're being attracted away from it, it kind of looks like a plus sign because it's starting to create what we call electropositive charge. It's not a full positive charge or a full negative charge. That's why they call it a dipole. It just means it's a direction of force, a direction of electronegativity. And actually, this is a good time to bring up a trend that literally this means the same thing as electronegativity. It's polarity. So when you have a difference in electronegativity, you also are going to have polarity. So the reason that we had a high difference in electronegativity was because we took something from the upper right side of the table and put it with something from the left side of the table. So there's a high difference in electronegativity. And that actually equals the same thing as polarity. For something to be polarized, what I like to think of is actually politics, because we say like in politics, we have far right and far left, right? So those guys are pretty different. The far right compared to the far left, they're very different. So they're kind of like charges, a negative charge and a positive charge. They're the opposite. But you know, in chemistry, negative and positive charge are attracted to each other, and it's not the same in politics. But it's a good way to think about what polarity means. If something's polarized, like polarized politics, it means they're very different. And same with chemistry, we have high difference in electronegativity. So high difference in the affinity for electrons. So one side really, the guys over here, they really want some negative charges, which that's their affinity for electrons. And these guys over here, they don't have a high affinity for electrons. So because they don't have that, they end up getting their electrons kind of shared unfairly with the other guys, and they become positive. So that's the polarity in the dipole. So let's do some practice. Right, so I'm just gonna draw a couple molecules. We're gonna do their dipoles. Okay, so with this first water molecule up here, it's the same as the OH bond that was by itself, but this time there's two of them, so you draw two dipoles. Now, look at these carbon oxygens. If you look at your periodic table, you'll see that oxygen is more to the right than carbon is. So our dipole is going to go towards the oxygen. It's more electronegative. Now carbon is more electronegative than hydrogen because it's more to the right than hydrogen is. So we draw our dipoles towards the carbon. And chlorine is much more electronegative than hydrogen. And here, this is our last one. Chlorine is more to the right than carbon. So here we draw the dipole going this way. And then we already know how carbon hydrogen's dipole is gonna look. For this one, it would be the same as the other. And oops, I made a mistake. Okay, that one points towards the chlorine, right? Because chlorine is going to be more electronegative than carbon. It's more on the right side of the table. And here's our last dipole. And so we said that electronegativity matched polarity, and that if something's polar, it's different on one side than it is on the other. So a little negative or a little positive, a little negative. We can also have, so this is intramolecular polarity. And it just means that this is the polarity between like two atoms. Intra means within a molecule. So if you look at this HCl, for example, here is the polarity. There's a partial negative charge on the chlorine, partial positive on the hydrogen. So this is a polar molecule overall. Oops, molecule. Okay. Now how about the rest of these molecules? I'm gonna switch to a different color. I don't like red. It's so strong. So this is our water molecule. And how can we tell if it's polar? Well, actually, let's start with this carbon dioxide. How can we tell that the carbon dioxide is polar? So the carbon dioxide here, you might want to automatically say it's polar because it has dipoles. But it's true that within the carbon and the oxygen here, there's a polarity. And within this carbon and oxygen bond, there's polarity because there's a difference between electronegativities. But the thing is, we have to look at this molecule all together. And what we see here is, yes, there's polarity this way, but there's also polarity this way. So they cancel each other out. So this is important because you need to know if a molecule is nonpolar or polar. So this one's going to be nonpolar. And I'll go over the reason why after we identify all of these. So here's H2O. Is this going to be polar or nonpolar? So we have dipoles. This one's kind of tricky one, I guess. So we have dipoles and they're going towards the oxygen, right? So they're both, so this one is going left toward the oxygen and this one's going right. So left and right cancel out, right? So we already have canceling out, but they're both pointing up. So this is going to be polar because not everything cancels out. In order to be nonpolar, you have to have everything cancel each other out to be nonpolar. And this, what happens is you have these bonds go this way, so the left and the right force cancel out, but the upper force doesn't. And this force is coming from the electrons, right? Because electrons have energy. So this is a polar molecule. Now in this one, we have this going up. Oh, this, I always do this. This going down, this going up. So these cancel out each other, and this is left, this is right, these cancel out each other. So this is nonpolar, this is methane, famous nonpolar molecule. And we already said this was a polar molecule because this is just one dipole. And how about this one? It's a little bit tricky. So here, what I could say that this is going right and up, and this is going left and down. And then you see that up cancels down and left cancels right. Or you can just look at them and just kind of tell that they're diagonal forces. So once they meet each other, they're going to have equal and opposite forces. So that's two ways to look at it. Here, there's no polarity between these carbons because they're the same molecule, so they share equally. I mean, they're the same atoms, so they share equally. And here we have the same thing, the diagonal forces canceling out, or you can just say to yourself, up left, down right. So this is actually nonpolar. So that's the important thing about drawing your dipoles. I always recommend doing it. But the reason these are important is because what you'll see is that in chemistry, polar molecules like to bond with polar molecules, and non-polar molecules like to bond with non-polar molecules. And you'll see why, maybe not in this video, but you have to know that polar bonds with polar and non-polar bonds with non-polar. So let me show something now. So I said polar bonds with polar, non-polar bonds with non-polar. Let me show an example of polar bonding with polar. So in general, first we want to ask why molecules / atoms even bond in the first place. What makes them go together? And the answer would be forces. Oops. Place. The answer is attractive forces. They're attracted to each other. Their opposite charges, even if they're partial or negative, attract them to each other. So let me draw a polar molecule like H2O and show why it bonds with other molecules like it. So this is actually exactly how water, this is exactly how water is formed. So you see how I'm drawing the oxygens by the hydrogens? Maybe you can guess why I'm doing that already. And draw a long chain of them. So this is how we get phases, actually, is stuff that's polar bonding with stuff that's polar, or stuff that's non-polar bonding with stuff that's non-polar through intermolecular bonds. So then I'm going to draw yellow lines between every molecule. And these yellow lines are intermolecular bonds. Earlier, I referred to intramolecular bonds. That's inside a molecule. Like this OH bond here is intramolecular, but these are two different molecules, so this is intermolecular, I'm sorry. The way I remember it, not to forget, is like, I think of biology, and bio, intramolecular is the fluid inside of a cell, and intermolecular, it's between cells. So that's how I like to think of it. Did I say intermolecular? I mean interstitial fluid and interstitial fluid. Yeah, that's the fluid in a cell or outside of a cell. So between the cells, actually. So these are intermolecular bonds happen between molecules, and these bonds keep the water molecules together. So this is liquid water. And it creates, so this is how phases are created, but we can also break phases. So if we just add some heat to this, and heat is energy, always remember heat isn't just heat, it's energy. It's a representation of energy. So here, if we add heat, we can actually break all of these bonds. So these are attractive forces, right? So you think it's easy to break them? It's not. Sometimes it can be if they're not strong bonds, but hydrogen bonds are actually pretty strong. So we have to put some good amount of energy in order to pull them apart. Like two things that really want to be together, we're putting energy there to pull them apart. Kind of like magnets. Magnets, they actually uses the exact same concept. There's a positive and a negative charged magnet heads, and you have them next to each other. You need to pull them apart. It's not easy. You have to put some strength in it, and that's your energy, that's your work. So we're putting in energy and work to break water apart. And you know, when that happens, we get separate H2O molecules, also known as gas or water vapor. So this is what happens when you're making pasta and you boil the water, and basically you have your liquid water and then it turns into gases. And these gases are further apart than the molecules in the liquid were. So the molecules in the liquid were closer together because they were bonding. Now these guys, no bonds. So actually boiling and causing vapor to arise is the process of breaking intermolecular bonds. Breaking intermolecular bonds. So gases have no intermolecular bonds. So that's basically why molecules and atoms bond. It's because they're attracted to each other, and we have to apply energy to get rid of this attraction, or overcome the attraction, because the attraction itself has energy and we need to apply some energy to get rid of it. So let's show what that means. So here's a solid, here's a liquid, here's a gas. I'm going to show this in a couple ways. So solid has nice intermolecular forces right next to each other. Liquid, you start to apply some heat to some ice or something, these start to get a little bit more further apart. And they still have the forces, but they're less strong because now they're separated by more distance, because the heat that you applied has pulled them apart a little, but it's not enough to pull them apart completely. Now, gas, you've pulled them apart completely. These are unbonded, no more intermolecular forces. So these little dots are individual H2O molecules. Okay, so what's happening here in terms of, like, let's put it, we know what's happening, but let's put it in terms of chemistry and the language that they use. So as we go this way, we have increasing kinetic energy. If we were to go from a gas to a liquid to a solid, we have increasing potential energy. Because when these molecules are like put together in a solid, they only have potential energy. They're not moving. And kinetic energy is the energy of movement. So once we apply heat, we transfer potential energy to kinetic energy. So it's the same energy, but it's behaving differently. So in between all of these molecules are the bonds which have energy in them. When we apply heat, we're transferring that energy. So every time we apply heat, now there's less potential energy. And in gas, there's like no potential energy. These guys are zooming all over the place. So we've broken the bond completely. And now the energy which these guys had in their bonds has turned into their individual kinetic energies. So together they were like stable, and that stability was a form of energy that could have been released at any time. But when they're separated, they're less stable because they don't have each other. They were attracted to each other, and that's what made them stable, was the fact that this guy was balanced by this guy's opposite charge. Now there's not really as much stability. So what happens is you have more unstable state, high kinetic energy. So if you get this, you're pretty good. You're pretty good. Just understand that there's energy in bonds based on the difference in electronegativities, and they can be released or reformed at any time. So like if we wanted our gas to go back to a liquid or go back to a solid, all we would have to do is increase our potential energy, and that would be by forming bonds. Okay, and this would be breaking bonds. So there's like some words you have to know, like when a solid goes to a liquid, it's melting or fusion. When a liquid goes to a gas, it's vaporization and stuff. But I will let you guys look at that on your own because it's just memorizing words. Let me clear this real quick. So rank, let's do another question. Let's rank these. We have HBr solid, HBr liquid, and HBr gas. So which has the most potential energy? And if you said HBr solid, you would be correct. Now for the kinetic energy, if you said HBr gas, you would be correct. This guy, HBr liquid, has a mixture of both. So let's go to and do something else. So that's pretty much it. I'm just gonna go over the example I just did, but this time just with water instead of solid, liquid, and gas. Make it less like abstract. So this is liquid water in a cup. This is ice. And then here's some vapor, some water vapor. So as we go this way, we have to absorb heat because the bonds of the solid require energy to break. So the ice absorbs heat and becomes liquid. And then as we go this way, we absorb more heat. This is boiling, right? We absorb more heat to break those bonds. The opposite way, we would have to release heat. The way we release heat is by reforming our bonds. Release heat. So when you absorb heat, it's something called endothermic. And when you release heat, it's something called exothermic reaction. That's just the name of the reaction. Don't worry about that too much now. Yeah, that's pretty much it for this. There's a lot in it, but thank you guys and see you guys later. I'm gonna figure out how to end this.